Hello everyone, welcome to video 8 of chapter 4. In this video, we will present the main theory on duality and we will go through the proof. So this is theorem 5, duality theorem. Here's the statement. Suppose either the max or the dual problem, either of them has a bounded solution. Then so does the other problem. And it holds that the max of the z equal the mean of the v. So basically the theorem actually stated two situations. One is if the max problem has a bounded solution, then the mean problem, which is the dual, which is also the d, would have also a bounded solution, and the max of z would equal to the mean of v. On the other hand, if you suppose that the problem d, the main problem, has a bounded solution, then the max problem will also have a bounded solution, and this conclusion still holds. Let's look at a proof. Okay, so we now prove the part 1 of the statement. As I just said, we would assume that the max problem has a solution, and then we will show the rest of the statement. Okay, so now let's assume that max has an optimal solution, which is attained at x naught, such that ax naught is less than b, x naught is bigger than 0. That is just saying that x naught is a feasible solution. And then this is an optimal one, which means this is a maximum. Then I also have the following. That is c dot x will be less than equal to c dot x naught for this x naught that's stated up here. And this relation holds for any feasible solution x. What does it mean? It's a feasible solution. Well, that means ax is less than b and x is non-negative. Okay? So this inequality holds for x naught that's given there, and then for any x that's feasible. Okay, so the max problem, we can introduce slack variables and we can write it in standard form. So instead of maximizing, we can write minimizing the negative of c dot x, which is negative z, that's what we want to minimize, such that, and ax less than b can be written as ax equal b, and by adding a slack variable to each constraint. Okay, and then now I have the variables we start with plus m slack variables. They are all restricted. Okay, so for this we're going to call this star circle. So recall that by adding slack variables we could have converted a standard problem, actually a max problem, as we are writing it in the standard form, and then conveniently it is also in a canonical form. So we observe that this is in fact already in canonical form. Okay, now for the discussion, now we assume that the vector b is non-negative, bigger than equal to 0. And the rest of the proof will be focused on this case, similar to what we did for the simplex theorem. And the general case where b could contain negative elements is left as a homework. Okay, so if b is bigger than 0, then the star circle, the LP problem, is in canonical form because the basic solution will be feasible. Okay, and the basic variables are exactly the slack variables that we add. Now we invoke the theorem on simplex method we covered previous in this course. It says that in this case, then there exists a sequence of pivot that would complete the problem. Okay, so exactly how they are being pivoted, we don't know for sure now, but we know there exists such a sequence. Okay, so let's put up the tableau. So this part here is the initial tableau. We put it in this form so it's clear that this is the initial max problem. These are the slack variables, now are the basic variables. That's the right hand side. And what is here is the original form of the objective function with these c's. Okay, and then you choose various steps of pivoting at the end. The after finite many of them, the process will end, and the objective function, the row, will look like this. Let's denote these coefficients r1, r2 to rn, and these constants here, let's denote it s1, s2 to sm. Okay, and then this box here will have a number, and this is c dot x naught, because we're assuming that's the optimal. X naught is the optimal. Okay, so this is what you would get. So let's call this row here row labeled with a double star in the bracket. Okay, what can we say about these coefficients? Okay, so first let's record. So we are minimizing negative z in this problem here. So we now have negative z is equal to the minimum of negative z is negative of here, which is negative c dot x naught. And secondly, since these coefficients are the coefficients in the objective function form at the optimal. So recall the simplex method theorem. When this is reached the optimal point, we shall have all non-negative numbers here. So in particular, all these ri's will be bigger than or equal to 0. I run from 1 to n to indicate that. And all these s here, we call it index j, j from 1 to m. All of them are also non-negative. And in that case, this would be the optimal. That's the end of the algorithm. Okay, so we have all of these. Okay, so the coefficients, the s here, that's the one for the slack variables. Now we're going to form a vector. We call it y naught. That's simply collecting s1 to sm transpose. So this is a column vector. So we know from the discussion on the previous page that all of these are non-negative. So it's bigger than or equal to 0. Okay, we now make two claims, A and B. Claim A says A transpose times y naught is bigger than the C vector. And claim B says B dot y naught equal C dot x naught. So let's take our time and prove these claims one at a time. Okay, let's first prove A. Indeed, so let's recall that final row in the tableau, which we labeled as double star. By that double star, that means we now have a new form of the objective function, which can be written as this. Okay, so r1x1 plus dot 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 rnxn, put the coefficient with the x with variable, and also the s 1 is xm plus 1, so on to Sm is xn plus m. You add them all up, it should equal c dot x naught, the optimal value, minus c. And let's call this relation triple star. Okay, let's compare this form of objective function with the original form for the max problem. There we have this form, so negative z equal to negative c1x1 minus all the way to cn xn, right? So the original is z equal to the plus of it, but then we write it into a minimization problem. We put a negative sign overall. Okay, so if we compare these, we see that in, let's call this one single star. In single star, I have only terms x1 to xn. I don't have the slack variables. While in the triple star form, I have all these non-zero slack variable, possibly non-zero. Why? Where do they come from? Well, we see that these terms are obtained by pivoting, right? So during the pivoting process, we multiply some constraint by some constant, and then we add it on top of the original form of the objective function, and then we get these terms, which are not here. Okay, so these arguments basically lead to the following statement. This means, okay, we can summarize the pivoting process in a specific form effectively, and we could think that I could take each constraint and effectively each constraint is multiplied by some constant. I call it T1, T2 to Tm. Okay, so there exist these constants such that if I multiply them, one of them on each constraint, there'll be m of them, and then together with the original form of the objective function, then I have m plus 1 equation, and if I add them all up, and this will let me get equation triple star. Okay? So what are these constants T1, T2, and Tm? Well, we can compare this process with the triple star form. Let's look at the coefficient for xn plus j. That will be the jth constraint is multiplied by tj times xn plus j. That will appear in triple star. And where we denote the coefficient actually sj. So basically we have tj must equal to sj for j from 1 to m. Okay, so we're now going to write tj simply with sj. Okay, and then let's look at what happens to the coefficient for x1 term. So the x1 term, the final coefficient in the objective function, will be the coefficient of all of these x1 terms add up, right? So R1 will simply equal to, now T1 is S1, S1 times A11 plus dot 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 all the intermediate terms, and Tm times Tm is Sm, Sm times Am1, and then minus C1. That will be the R1, and then we already know that R1 shall be bigger than equal to 0. Okay, so this inequality here, I can move the negative C1 term to the right hand side, and I obtain this inequality. Note that the index x1, the 1, appears as this one here, am1 and the n1 and c1. So we see that we can also look at the term x2, x3, all the way to xn, and for each of them, I will obtain an inequality with a different index. Okay, let's look at in general what happens. Let's look at the term xi, following the same argument as we did in the previous page. I obtain this inequality for I from 1 to n. Okay, so on the previous page, what we have written is I equals 1. So replace I with 1. That's the inequality for the x1 term. Now we have it for the general I term. So what we have here is n of such inequalities. We can just write it out. We'll have n of them with the c on the right-hand side. If we look at the left-hand side of these n inequalities, and we treat the s, s1, s2 to sm, we call that's the vector y0. We denoted it. If we take that out, and the coefficient matrix is exactly A transposed. So this simply means A transpose times y0 is bigger than C. And that is exactly the claim A. So we just proved that. Okay, now let's prove the claim B. We can simply now look at the right-hand side of this above discussion. That is, these m plus 1 equations, I add up to obtain the new form of the objective function. If I look at the right-hand side, what I have was, so the b1, b2 to bm is now multiplied by these s, right? s1 times b1 plus dot 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 to sm plus bm, this would add up to the term that is the constant term for the objective function, which we know that at that point it's the optimum, so it's c dot x0, where x0 is optimal. And look at the left-hand side. What is this? Well, this is the dot product, b dot y0, where y0 is this vector for these s's. So we have shown that b dot y0 equals c dot x0, and that is exactly claim B. Okay, now we have established the claim A and B, and then we will move on to continue with the rest of the proof. Okay, so since I have AT y0 bigger than C, and y0 is bigger than 0, and then I know y0 is a feasible solution to the dual. And furthermore, by the claim B, we have that the v value there is b dot y0 exactly equals c dot x0. That's what we proved there. And now we apply corollary 3, which we proved in the previous video. And there it says, if this holds, then the y0 is where v reaches the minimum value. Okay. So this completes the proof for one way. So that is, if the max problem has a solution, and then so does the dual, the mean problem, and the max and the mean value are the same. Okay, and I'm just saying here now, the other part of the argument for the other way around, assuming that the mean problem has a solution to show the max problem also have a solution and the max and mean are the same, this can be proved with a completely similar argument. Okay, and we will not go through the detail. I'll leave it as an exercise. Okay, so hope you enjoyed this, and I'll see you next time.